Today we're quickly going to look at some graphs of functions, specifically of polynomials. Now, remember, a polynomial is any function f of x which can be written this way: a(n) times x to the n plus a n minus 1 x to the n minus 1 plus so on, with a lot of terms ending with some constant terms. So all terms are of the form some constant times a power of x. Now for now we're going to require that all our coefficients here have real values, otherwise things get quite a bit more complicated. Now the first polynomial, of course, that we're all familiar with is the function y equal to x, which is just a straight line to the origin, and its negative version y equal to minus x. Now you can do a lot of interesting things with linear functions. They can just basically move up and down and left and right, and they will really not concern us at the moment. And the first semi-interesting function that we're looking at is the quadratic function y equal to x squared. And we have the negative version, y is equal to minus x squared, which is just this function turned upside down. Now again, this function can only really move around a bit. By changing our coefficients, we can stretch it out, make it wider, make it narrower. So for instance, we can have a quadratic function there, let's say with roots 2 and 3, so that'll be a function of the form y is equal to x minus 2 times x minus 3. Another interesting case is when we don't actually have any x intercepts at all. So this is, of course, when our function is of the form ax squared plus bx plus c, where b squared minus 4ac is smaller than 0, also known as our discriminant. Now one thing I want you to notice here is that a linear function always has one x-intercept. Now what happens in the case of a quadratic function? We can have one intercept. In this case we can have two intercepts, or we can have no intercepts. But in the case of one intercept, we actually kind of have two that just have the same. So we say that the function has an intercept of multiplicity 2. So that's actually x minus 0 times x minus 0. Now, things get a lot more interesting once we start going to third-degree polynomials. Now, the basis for all third-degree polynomials is just this function here, y equal x to the third. And the two basic ones we're going to consider are y equal x to the third and its negative version, which, as you can see, is just the mirror image. If you look at the x-axis of y equals to x to the third. Now, of course, this very simple case is not usually what occurs, and we usually have much more interesting third-order polynomials which look like this. But they're really just an adjusted version of the original polynomial y equal to x to the third. If you look at our graph of y equal x to the third, and you look at this supposedly more complicated one, you can see that they actually, if you just tilt your head a bit, look almost the same. In fact, if we just pulled this part down a bit, these two functions start looking a lot alike. So you can consider all third-degree polynomials as some version of y equal to x to the third, which has somehow been stretched a bit in one place, or perhaps lifted up in another. The same for y equal to minus x to the third. If your leading coefficient, that is the coefficient of x to the third, is negative, the function is always going to be some version of this. Now, we could have, such as in this case, 3 x-intercepts. We could have 1, which would look like that, for instance. If you only have 1 x-intercept there. But can you ever have none? Well, since the one side of the function always goes to infinity and the other side always goes to minus infinity, somewhere in between you must go through the x-axis. So we know that our third degree polynomial will always have an x-intercept. Now, it might have 2 if I, for instance, have a function like that, where it just touches the line, or it could have 3, as we have seen. Now, when we started with our original function y equal to x to the third, in order to get a function like this one here, we immediately know what form we must have. It's of the form of a minus x to the third function, so the leading coefficient will be negative, and it will be of the form, possibly with some constant in front here, x minus x1, x minus x2, and x minus x3, if we were able to factorize it properly. And in this case we have x1, x2, x3 in R. Now, in the case of a function like this one, where we have 2 roots, but you really have 3, but 2 are the same, you will have a function which looks like y. Now, if you look at the shape, you can see it's a positive leading coefficient. This function will be of this form. So one of the roots of the function is repeated twice, and that's why it only touches the axis there. Now, what if we have a function like this, which only has 1 x-intercept? Well, we will have something of the form, there's possibly some constant in front, but we're just writing down the general form. Oops, x3, where now x1 is a real number and x2 and x3 are complex numbers. Okay, now this could also be written in the form equivalently: x minus x1 and then some ax squared plus bx plus c, where b squared minus 4ac is smaller than 0. There our discriminant from high school maths comes in again. So we know that whenever we're given a third degree polynomial to draw, it's going to be of this shape if the leading coefficient is positive, or this shape if the leading coefficient is negative, where we can see, well, we're sometimes going to be allowed to deform it somewhat so it can look like this or like this, but it will be basically of this shape. So you can always know more or less whether the form of the function you're drawing is correct. Now, what about fourth order polynomials? So let's start with the basic one, y is equal to x to the fourth. This is just as uninteresting as the quadratic function and looks the same. It's just going to rise a bit more steeply, and of course the negative version will just be the reflection of that around the x-axis. But this function can get a lot more interesting if we zoom in on this bit here. Now, what you can think of is that function kind of makes an infinitesimal wobble there. And in fact, if you start adjusting the function slightly, that wobble is going to increase. So for instance, if we have a function of the form x minus x1, x minus x2, x minus x3 times x minus x4, where let's say all of these values are real, then you're going to have a function looking more or less, like that. Okay, we don't really care where that y-axis is at the moment, and if the leading coefficient were negative, our function would just flip over to the other side. So this gives you an idea of how all fourth order functions look. Now again, this could be changed somewhat by stretching and changing certain shapes, but in essence all of these functions are going to be the same with two bumps. Now, as in this case, for instance, where we have a stationary point which is not a local maximum or a minimum, the bump is just a flat bit. But you'll see you always have, for the positive leading coefficient, two parts of the function going to infinity, and with a negative leading coefficient you have two parts which go to minus infinity. And if your function doesn't satisfy this, you have drawn it wrong. Also, if you have more than two bumps here, well, I suppose you can call it three bumps if you include the middle one, you have not drawn a fourth order polynomial. And so you can go on. All of the basic shapes are essentially the same as the previous ones. Y is equal to x to the 5 looks very similar to y equal to x to the third. It just rises quicker and falls more quickly on this side. But now again, in there many more bumps are encoded. So if we deform this function a little, we could actually get something like this. Okay, now let's look 1, 2, 3, 4, 5, 6 roots, which means I haven't done a fifth order polynomial. Oh no, 7. I have done a seventh order polynomial here. So we know if to draw a third order polynomial, I can never have more than 5 roots, so that had to go up there. In the same way, one part of the function always has to go to minus infinity, and one part always has to go to plus infinity. So anything of this form, that first bump can be flat, then we have another bump, this one can go down. This will be a form of a fifth order polynomial, or of course its reverse. But you can never have more than 5 roots and never fewer than 1. And this kind of scheme continues for all polynomials. The graph of x to the 6 is again quite uninteresting. But as soon as we make it a much more interesting function, let's say you can factorize it as x minus x1 times x minus x2 times x minus x3 times x minus x4 times x minus x5 times x minus x6, where x1 to x6 are distinct reals, you're going to get a function with 6 x-intercepts. Now in this case, it has to basically have the same form as the original one, but with some bumps, which in this case are hidden in that part inside. So it will look like this, more or less. And that'll be any 6th order polynomial with positive coefficient. Will have two parts that head to infinity and could have anywhere from 0 to 6 x-intercepts, never more than that. And then the same for the negative version. It'll always look like that, and will always have one part that heads to minus infinity and another part that also does. Now this holds for all orders of polynomial. If you were to look at y equal to x to the 7, once again the basic shape is this, but we can have 7 roots. Now it has to start, if you look at the left, something coming up, and it has to end up with something going to infinity. And then all 7th order polynomial graphs are just variations of this. The bumps can be less pronounced, they can be flat, for instance. So it can look like that, but it's essentially just this shape, which is where some parts of it have been pulled up, other parts have been pulled down. It's as if you have a string which you can rearrange by pulling some parts up and other parts down, and this will give you the basic shape of any polynomial function. Therefore, if you're given a polynomial function to draw in an exam or in the assignment, you will know more or less what the shape is, and your main task is then just to make sure you can find out where the stationary points are, and if they are minima or maxima, and then to find out where the inflection points are, and just verify then when you draw it which parts of it go to infinity and minus infinity, and if possible find the x-intercepts. The y-intercepts are of course always easy to find. So you always have a basic shape in mind, and you can verify that your calculations are correct by considering this basic shape.